Our next guest says he's a recovering C developer in the embedded space. So he's going to talk to us about why he now uses Go in the embedded Linux space.
Welcome to FOSDEM. Welcome to this talk. I'm going to talk about Go. So the premise is that I want to convince you that you should use Go for your projects, for your next software project, for your existing software projects. My name is Zygmunt Krynicki, and these are the confessions of a recovering C developer. So before we begin, a little bit about me. I'm about 40 years old. I've been programming for about 30 years, including 20 years professionally. I've been using C for most of my life, then Python, and then for the last 6 years, I've been using Go. You may know me from my previous work, where I've been doing some public open source work. Currently, I'm a principal technologist at Open Source Technology Center at Huawei. And in my spare time, I really enjoy retro programming because it lets me get this insights into the technology I used to play with as a kid. So let's get to it. So I've split the presentation to several chapters. I'm going to talk about the world that we are in right now as software developers working with embedded things. Then I'm going to focus some time on Go tooling, about the tools you will experience by using Go, and about why I think these are really important. Then I'm going to give you a quick overview of the language. We don't really have time to get into the nitty-gritty details of everything that is interesting, both good and bad, about Go, but I'm going to try to do my best to convey the general feeling. Then I would like to spend a little bit more on one particular feature, which are Go interfaces, which I think are just fantastic, and they are a great improvement to virtually everything I do as a programmer. Then I have this small section about just the highlights of cool and interesting small features to the language that just make everything, again, a little bit better than if you didn't have them. And then we can open up for questions. So that's the agenda. I'm going to switch to a different... Okay, I'm going to switch to a different modes. Okay, so part one, the world. So my premise is simple. The world has changed and will keep on changing. And just as we moved from small microcontrollers to effectively small computers or really small servers, the complexity of the software running on top of these machines has changed as well, has matched the capacity of the new hardware. And in this complex world of software, maintenance and security have actually become more and more important than ever before. There's interesting new legislation around software updates. There's interesting new legislation around maintenance requirements on software vendors. And I think this will only be continued as a trend where we can no longer think of things we make as temporary toys, but as long-term support products that are actually important. If they fail, the failure is meaningful, not even as an inconvenience, but more and more so as actual danger. And we have to think about the tools we use to develop the software, because tools can vary and they matter a lot for the quality of the things we can produce. This is why I want to talk about Go tooling. I believe Go tools are a joy to use. They are well done, they are comprehensive, they reach to all the relevant parts of engineering. They are standardized. They have not, unlike some of the other technologies, they have not spread around as a zoo of third-party proposals that just keep reinventing the same wheel. Go is very cohesive in the sense that it provides a lot out of the box, providing a very rich and fertile ground for building applications rather than filling the missing gaps. I'd like to cover a couple of things that I think are just very important, especially from the point of view of writing embedded software projects. So the first thing is that Go is extremely easy to build with. If you've been using any kind of embedded programming environment, weird cross-compilers, very complex set of tools, so things like BitBake or the Yocto ecosystem, it's great that we have it, but it's really fantastic that we can just code without touching that until the very last moment when you need to just do the packaging. Go is extremely easy to build with. Go build handles your dependency, handles your cross-compilation, handles your configuration, and it's such a powerful combination when you think that effectively by installing Go itself, you have virtually all the tools you need to create programs for any platform. Ironically, plain make is actually still common in Go projects so that you can still install your programs in the desired locations so that you may copy additional files that you would like to have. But even that is not necessary. The fact that you can effectively just use the single built-in Go build command to pretty much do everything required for a complex project is a fantastic refresher coming from C and the plethora of complex tooling that has grown around it over the years. And if you're talking about building, the actual builds are very efficient. They're very fast. This is done by some clever design on the language and some clever implementations in the compiler. And this translates to very fast iteration. You can just build, test, and build or run your program in seconds, even for programs of considerable size. This is extremely useful. When I'm building my applications, I'm constantly writing tests, I'm constantly running them, I'm constantly trying things out. And if I were to think back to how I was doing things before, when the iteration was measured typically in minutes, it's just completely different experience. Especially when some of the other things integrate well with your environment. We're gonna discuss those as well. So once you've built your program, it's actually very easy to share. Go has a quite interesting method for handling dependencies and handling publishing. So with Go install, you can literally install anything that is publicly available. And unlike some of the other technologies, unlike some of the other languages, this is a highly portable solution. So it's very likely that you will be able to install something on Linux, Windows, and macOS alike. Obviously, there are exceptions. There are things that are platform specific. But it's very easy to create portable codes in Go. It's very easy to create portable applications and libraries. And like portable in practice, that things will just work fine and that people actually support other platforms. And sometimes you don't care about this, but it's really convenient when you have to. And the builds that come out of Go are most likely static binaries. There are some exceptions, but it's very easy to just create a single binary that is self-sufficient, standalone, and can actually be easily shared. And this translates to very easy deployment as well. So because of static linking, you don't have a runtime or interpreter or virtual machine that you have to depend on and provide as well. It's usually just one file, so it's extremely trivial. You don't have to think about where it's going to be located, how it's going to find its data. Go has a very interesting new mechanism to embed additional file systems within the binary itself. So even though you may require a large number of data files, for instance, you're building a web application that has a lot of templates, a lot of style sheets, and other things like that, you can actually embed all of that into your binary. So it's still going back to, it's just one binary you can copy, and this binary just works. And because of static linking is actually not linking to the C library of your platform unless you use CGO, which we'll discuss in a moment. So this means that you don't have this problem that sometimes you encounter in embedded programming where your code works on glibc but doesn't quite work on Muscle or other libraries, because that's just not a problem at all. You have a very predictable runtime behavior this way. And this is really great for both servers and containers and embedded programs, because effectively what you coded, what you tested, is going to behave exactly the same way on other environments, and it's extremely easy to prove so by just running it there. So cross-compilation is just a joy in Go. Forget setting up your cross-compiler, forget custom vendor patches, forget something that's broken, forget something that links to your host libraries by mistake, forget doing it in 20 different ways, depending on the subset of technologies that you may be very familiar with. C is just brilliant. You just set a Go OS and Go Arch variables, and you can just go build whatever you want for whatever platform you want from whichever platform you want. So this actually works regardless if you're running Linux or Windows or Mac OS, regardless of the CPU architecture. Go is very portable in this sense. You can also compile your projects for Android, iOS, and WebAssembly, although I personally have no experience with that. And unless you use CGO, which is effectively the bridge to use C code within Go programs, you don't need the external cross-compiler. So Go is really all you need for a good chunk of the projects I've been working with. So it's really that simple, 2 variables. And because the binary that you get out is static, you can just copy it and run it directly on your target. It's very convenient. I don't have a bullet point for this here, but I just want to mention it. Go doesn't have a preprocessor, and yet without a preprocessor, it manages to be extremely portable and offers a way to create conditional compilation by effectively selecting specific files to compile out of the directory using a convenient mechanism either by convention or by declaration. And this means that the standard library is extremely portable and it has implementations for all the relevant platforms, but this translates all the way to end-user programs and third-party libraries. It's very easy to create portable code in Go, mostly because the standard library wraps around the rough edges that just the platform differences are usually something you have to care about manually, so this goes away. But then if there's something that you have to do that is platform specific, there's a very simple and convenient way to express that as well. So this means the entire package stays portable. So going to dependencies. So Go is actually pretty brilliant on handling dependencies. This is something that has been added to the language since its inception, but now it's well established. So there's 2 things I need to explain. A package is just something you can import into your in a file that you're working on, and this is like something like an include statement. But if you want to actually depend on something, that you have to bring in the whole module. So a module is a set of packages. When you add a dependency to your program, you add the dependency on the module. And the place to get the module is actually arbitrary. Go does not have a central naming registry like some of the newer languages have gone with. You can put your code literally anywhere you like. There is a convenience central place that just indexes publicly available modules, but the path is essentially the URL. So it's very easy to publish programs either branded with your GitForge or with your company name. It's super convenient, and you don't have to there's no problem of name squatting. You don't have to think about reserving names up front or something like that. It's very practical. There's a lot more that I could say about the dependency management in Go. There's some very interesting things coming in 1.18, which is Go 1.18, the upcoming next release, that I think will be actually very meaningful to Linux distributions, because there will be a way to kind of do what distributions try to do by forcing the single library across all the programs using that library in a scalable way. But my point is that there's a lot more depth to it than that. But we don't have time to go into it. But I think the overall aspect is that it's just well done. It works very well in practice, and I think you'll enjoy using it. And again, there's a lot more than I have the time to cover, but I'm just going to mention some quick highlights here. So there's a standardized way to test, benchmark, and fuzz test your programs. Since Go 18, at least for fuzzing, everything else was available before that. So this means that you can expect very standard behavior from your own code, from third-party code, from standard library code on how you actually want to measure correctness. There's great tooling around that for all kinds of interesting things like coverage reports, and fuzzing is in particular very interesting because I think it's the first mainstream language that has it built in. So I think it will be a very interesting new development for library authors to harden the libraries even more by effectively adopting this technology to find bugs that may be lurking beneath the surface. Another very important thing in practice is that there's a standard way to reformat all the code in Go. So this means that effectively, no matter which project you look at, it has a very standardized look and feel. Both in the simple things about how the code is laid out, but this actually goes deeper. Obviously not automatically, but there's a standard naming scheme for things in Go, and I've seen pretty much all the projects that I've interacted with adopt that. And this means that Go is just super uniform. No matter where you look, it's not difficult to get into new code. It's not difficult to learn how other people wrote something. It's not difficult to explore the standard library. It's extremely readable. Unlike what you find in C, where there are multiple prevailing styles, some of them are, at least personally, I find them kind of ugly and difficult to follow. So I think this is a great simplification to making the entire language platform accessible to people. And lastly, on tooling, there's an official language server. So if you're not familiar with what that is, it is a modern way to handle programming languages within an IDE or a code editor. So unlike the previous approaches where the editor would have to figure out, oh, this is a language like that, this is how you parse it, this is how you can apply some syntax coloring to it, and maybe I have a little bit of understanding of what it really means beyond the superficial shallow syntax. Language server is effectively a part of the compiler running as a service within your system that looks at the project you're developing, keeps its internal memory structures up to date, and offers services for the IDE. So no matter which editor you prefer, if it supports language servers, and pretty much all the commonly used things do, you can have a great coding experience by having deep language understanding, by having deep refactoring features, like symbol renaming across everything, like moving things around in a way that it preserves the semantics. It's very convenient, and as the project grows in complexity, I think it's just fantastic to have this available in such a universal way, and coming from the people who make the language directly. So that's the tooling side. Okay, interfaces, my single most precious feature in Go. And if I could actually get interfaces in C without anything else, that would be, I think, the single biggest improvement to the language it ever had. Anyway, let's get into it. So interfaces are types. Just like you can have a value of a type like int, you can have a value of a type which is an interface. And interface is literally a set of methods, just the signatures of methods, the set of method signatures. So when you have a value of an interface type, you can effectively call one of these methods and nothing else. And unlike in some of the other languages, any type that has this set of methods actually is set to implement this interface. So you don't have to name this up front, and you don't have to, it's not explicit, you don't have to explicitly code this in your program, and you don't have to actually use a specific name. So the name of the actual interface is just not important. It means you can have multiple interfaces which are effectively the same interface, and not introduce arbitrary dependency between part of a program just because they happen to need to pass the kind of same looking things. And interface values are actually small pieces of memory that you put on stack. They're really pairs of words, one describing the type and one describing the value, typically a pointer if it's something larger, or maybe the value is actually baked into the interface value itself, or for things like that fit in a word, which translates to efficiency. So it's really efficient to call methods through an interface. It's roughly the same as C++ virtual method calls, and it's prevalent in the language. So let's look at a quick example. If you are not familiar with Go syntax, it says there's a type called greeter, and the type happens to be an interface, and this interface has one requirement. There is a hello method which returns a string. Obviously you can have more methods in an interface, but it's very typical to actually have just one. So again, any type which implements the hello method, which returns a string, implements the greeter interface without declaring it. So there's no equivalent for implements in Java. And the name of the interface itself doesn't matter. So if there's an interface called helloer, with the same method, it's the same interface in practice. Code will accept it identically. And this really decouples things around everything in Go. I will just do one example here. The standard library has the IO package with a writer interface, which effectively says, here are some bytes, write them, and returns the number of bytes you got, and an error in case something failed. And another package in standard library, the fprintf function from the format package, takes a writer, a format string, and an arbitrary collection of values, and does what fprintf in C would do. But the beauty in it is that you can provide arbitrary writers. So you can provide a file or a pipe or something like a network socket or something elaborate, something that logs to screen, something that paints it or prints it. And it's extremely practical not to duplicate the logic of formatting by just providing arbitrary interface for writing. And there's lots of interfaces within the standard library for I/O, for a lot of other things. And it's really convenient to use in practice, and it's type safe, and it's quite performant. And if you think about the fact that interfaces are just sets of methods, then the question arises, okay, what about the empty set? Well, the empty set is the, I think, void star equivalent of Go. It's fully type safe, and there's a lot of practical uses for it. You can pass any value through the empty interface. You can recover the actual type in a type-safe way. So you can say, okay, I got an interface, but I was really expecting a couple of different things. Maybe I got a string. So this is the case for a string. Maybe I got an int. Maybe I got something else. And you can do it in a type-safe way. You can also use the reflection package to actually look at the thing you've got and explore it at depth. You can just do arbitrary operations on it through the reflection package. So it's very practical. It's, again, very prevalent in Go. And some of the things that it is doing are going to be improved with the addition of generics in Go 1.18, because some things that used to accept an interface will be complemented by making that interface something that is declared at compile time. So you can think of generic collections. You can think of a lot of examples where you can parameterize something by a type. And currently that's done with the empty interface. But this is a very powerful method of providing this dynamic aspect to the language. Like even the printf function we looked at before, it takes a collection of values to format, and all of them are provided as an interface. And the logic inside the format package understands how to format different things depending on their type. It can offer, like the types that the values that you pass can offer special methods that integrate with the format package so that you can print something custom in a custom way. This provides a lot of flexibility, but again, in a very type-safe way. So this finishes the key highlight I wanted to have around interfaces, because I think they're the most fundamental thing that improves programming at scale, making it modular, making it testable by making replaceable pieces, interchangeable pieces, and loosely coupled pieces. But now I would like to spend a little bit on just highlighting some smaller features of the language that you don't have to be as large and complicated, but provide tremendous value. So reflection, we mentioned this interface. Reflection effectively allows you to look at anything that you've been given through an interface. So you can look at the value, you can look at the type. There's a whole array of methods to look at specific parts of everything possible in Go, like reading an array from a given index, writing to a map, working with channels, working with structures, calling functions, all of that. And that's obviously type safe and extremely convenient. And the standard library uses reflection in several places. Like, for instance, there's a library. There's a package for marshalling values as JSON, and you can provide it anything, and it will provide correct JSON output. And it's implemented using reflection, so it doesn't require any coding on your part, but it's just going to look at the type at runtime, and it's doing that still in a statically compiled, statically typed language. So struct tags, I mentioned this earlier, and it goes hand in hand with reflection. So reflection lets you read struct tags, and struct tags are just strings associated with distinct fields of a structure. So here we have a simple example that type is a person. Sorry, there's a type called person that is a structure. It has two fields, Nick and away. One is string, one is bool. And there's some metadata for how you would like to represent this as JSON. For instance, the away field should not be mentioned if it's empty, or like if it has the 0 value, has the default value, which is false for Boolean. And you can read structure tags through reflection. There's a mini language inside, and this is all accessible through the API. And the JSON package I've mentioned has a Marshall function which actually uses this. So we're providing an instance of a person, and it's going to look at that instance, going to look at it. Okay, it's a structure, so I know what I need to do. It converts to a JSON object. It's going to look at the fields it has. It's going to use those structure tags to get the hints about what it's supposed to do. And this is extremely practical. I've been using this for JSON, for YAML, for dbus, for INI files. It's extensible. You can code your own library which uses this. It's very practical. It's very easy to create something which is declarative and conveys the message. Like doing API reviews using those structures with struct tags is very convenient. And again, it's a small thing, but I think a small gem. There's the 0 values. So this is so simple. No uninitialized memory in Go. Go does not have an initialized memory. Everything has a default value of 0 for the type. And a lot of these, there's a lot of convention around saying that your type should behave in a meaningful way as a 0 value. So it should not require additional initialization. Maybe one example is like the standard library buffer, like a string buffer or a byte buffer. When you put it on stack, you just declare a variable of this type. It's already a correct buffer. You can start using it as a buffer. You can start writing to it. You can maybe start reading from it, although it's empty. It doesn't require additional steps, and this just makes everything a lot easier. You know, there's no uninitialized memory, and the things will behave correctly without explicit additional steps when they are not required. I mentioned symbol visibility earlier, and if you read the slide and you think, what is this? This is kind of crazy. Then you know it may be a valid reaction for something as radical as this, but capitalization defines visibility of symbols within a package. So everything that is capitalized is a public symbol. It's part of your public API. You shouldn't break it. You should document it. And everything that is not capitalized is a part of the internal implementation that is not accessible from outside of the package. And the compiler and the linker ensure that nothing like that happens. And you can freely refactor those. You can freely change those. You can actually, while writing, you're painfully aware of the subset of your API, which is public, that you have to pay more attention to. And I think this is so important in practice because, unlike in many other languages, I found a lot more attention to what the API, the public API looks like, and a lot more attention to stability because of this mechanism. Just makes it very in your face as a direct approach to handling this problem. Go has another small gem, which are called deferred calls. And there's a quick example here. We open a file, we check if we managed to open it, if there's an error, and then we defer close it. We call defer, we say defer and then fclose. So it really means that no matter what happens within this function, how we return, there could be multiple return paths out of the function, we will always close the file. And that's really it. It's coupling the acquisition and deallocation or release of the resource in the code, by just close proximity. It's easy to read a function from top to bottom and see if it's missing something by just looking, okay, you're getting something here, you're checking for your problems, you're checking for you're releasing your resource later, that looks good, carry on. It's much easier than the equivalent that you often adopt in C, where you have to have a lot more duplication of the cleanup code, or specially handcrafted cleanup tables with goto and specific loops, or by using non-standard extensions for the attribute cleanup. This is a little bit more generic. You can put a lot more than just a function here. You can literally code. You can put a whole function that you would like to contain your cleanup logic, and that's super convenient in practice. Just because it's, again, the proximity of the acquisition and the release of a resource. So another small gem that has been added to the language recently is the embed package, is embedding files within your program. So within your library or within your your program, whatever you're writing, you can say that you would like to embed some files from the file system into the binary. And you can choose to embed them either as bytes, as a string, or as the entire file system. So in this example, you can see how a hypothetical application would embed some images, some templates, and some an index file for a web application. And we get something which looks like a file system. This is an interface. It looks like a file system. It has an open method for opening files. You can read directories. You can read specific files. And this is just so convenient because, again, going back to the whole deployment story, this means that you can now embed pretty much all of your data inside the same binary. So just updating one binary updates everything in a atomic cohesive step. And I think it's just such a small but fantastic feature. I just needed to highlight it. So what is my message? I would like you to consider Go for your projects. Go is extremely practical, easy, safe, and scalable. It has a fantastic standard library. It's got great tooling and a nice ecosystem of third-party libraries and programs around it. So that's my message. Get started with Go. If you want to learn about Go, there's a fantastic web resources that's provided. Go.dev. Everything is in one place. Really give it a go. Thank you. If you have questions, now I will cut the video and we should do some live questions. If you would like to talk to me, yeah, I'm available on IRC and Twitter. You can find my code in some of the places as well. And thank you for your time. Thank you for listening. That's it. Bye-bye. Okay.
Thank you, Zygmunt. You really convinced me into looking into Go in the embedded space. So, to the audience, please refrain from any fights about whether to use Bazel or not to use Bazel. Please take those to the Java dev room over there. Thank you. I have questions, and if you still have questions, you can still type them here below. Well, it's gonna talk about sizes. Have you seen any limitations about the Go memory management for the embedded space?
So if you think about the classic embedded, like with TinyGo, where it currently is exploring, I have not looked into that much. I was mostly looking into virtually miniature servers that are running Linux and have way more memory than you would probably dream of on the desktop. So there I did have some issues with memory, and mostly about ambient memory pressure, where you just have a service which just takes a fixed amount of memory, even though it's not doing anything. So you have to be mindful of what you actually keep in memory on top of what the language runtime requires you to keep in memory. And there are a couple of approaches on how you can do this. You can maybe split your binaries into smaller chunks, paying the tax of additional binaries, but then having the option to load just the right binary at the right time, and as it executes, you will use the memory, but then the memory goes away. Or by just debugging your application, maybe there's something not technically leaking, but not doing the thing you expected. So there's a range of tools where you can explore the contents of the memory at runtime of a running process through a there's something you can easily include into any Go binary and then look at it remotely. So this can tell you roughly what is inside the process at runtime. And there are similar tools which you can take a look at the binary size. So okay, why is this binary such large? Thing. So for the memory, I have not personally run into something that would be critical, but I did run into a project where Effective was trying to slim it down to such a small device that, in my opinion, it was no longer practical to go with Go, because effectively you were building on a device which would be obsolete in my point of view.
I'm going to stop you because our time is over. There is a breakout room for everyone who has additional questions. Go there, follow the link.
Yep.
Just